Hello. Okay, hello everyone. Let's welcome our next speaker, Shatola. Shatola from Kleros. Kleros is a decentralized arbitration service for disputes of new economy. And he will bring us via bridge. Let's welcome Shatola.
All right, thank you. So I'm a developer at Kleros, and we've been building a bridge primitive that we call Vea. So to give you a little bit of motivation, Kleros is a dispute resolution mechanism. Why are we developing a bridge? So you don't need to understand the full details of what Kleros does, but I'll just demonstrate motivation for why Kleros needs a bridging solution and how it can apply to other projects. So one of the problems Kleros solves are real-world problems. So imagine you have some client, Alice, in Taipei, who wants to hire a web developer freelancer in Argentina. And instead of paying Bob, the freelancer, directly, they're going to pay, Alice will make the payment to a smart contract that holds the payment in escrow. And Kleros is an arbitration mechanism where if either party has a dispute, Kleros will resolve it. So Kleros is an arbitrator. But you can imagine any sort of Oracle input being able to resolve this dispute. You need some sort of off-chain information, and you need to bring that information on-chain. So in this case, Alice wins, for example. So Kleros was built for, well, it launched 3 years ago in an environment where gas was very cheap, maybe 1 gig away. But clearly, in the bull market, many applications were priced out of mainnet. And so now, with the rollup-centric roadmap, how should oracles adapt to a rollup-centric roadmap? What happens when applications that query your oracle live on different chains, different networks, different rollups? And so just to demonstrate the point, Kleros, for example, is designed for some high-volume, low-value use cases. So the escrow amount might be 100 DAI, in which case, if you need to query an oracle that lives on a different chain, in order to do cross-chain communication, if you use native bridges, then it takes time, but it's also costly. So the cost of going through mainnet might price out most of your applications. So how can we solve this? One idea would be, hey, I'm just going to deploy my protocol on every single chain. This has drawbacks, because if your oracle derives its security from economic security, when you deploy in multiple networks, you split your liquidity, and you split your security budget. So the idea is to choose a home. Choose a home where you concentrate your economic security. So in Kleros' case, the oracle we have is deployed on mainnet and on Gnosis chain. And our roadmap is for the version 2 to deploy on a single home chain. And by the way, home is where your node is. So currently we're comfortable having deployments on Gnosis and mainnet. Those are permissionless systems, because currently all of the rollups are memes, and their systems aren't permissionless, and you can't participate in the fraud-proof mechanisms, whether it's optimistic or zero knowledge. All of them are multi-sigs. All of them are proof of authority with more steps. But we've been shopping for a new home, and there's a few interesting neighborhoods. There's a few popular neighborhoods. These neighborhoods happen to be optimistic rollups. So, Arbitrum and Optimism are the most popular neighborhoods. But there are some risks involved. So some of the drawbacks, of course, optimistic rollup. If you have an oracle deployed on an optimistic rollup, doesn't have to be Kleros, just imagine any sort of oracle. You have a 7-day delay, and you have a cost of doing some cross-chain communication. So how can we solve this? Well, Kleros has a solution. So we've been building this bridge primitive called Vea, and we can bridge messages in about 2 days. How does it work? So Merkle trees are involved. So on the sending side, so on Arbitrum, there is a Merkle tree, the incremental Merkle tree that maintains a compact state of all messages sent through the bridge. So in this case, the tree has no fixed depth. The leaves are double hashed. We're using Ketchak hashes. This isn't for any sort of ZK application. We don't need a fixed depth, but an incremental tree is most efficient in this case. So how does it work? Well, we split time into epochs. So you could imagine an epoch is like an hour or so. So the idea is that on Arbitrum, on the sending side, anyone can sort of save the state of the bridge, save the Merkle root in a storage slot, in here, for example, in the first epoch, in epoch 0. And sometime later, after a delay, on Ethereum, someone can make a claim after a delay. So right now, we think a safe delay is 30 hours. Why 30 hours? Well, Arbitrum the optimistic rollups don't operate synchronously with mainnet. The sequencer actually has some power to backdate transactions 24 hours. So because of this, you might not know the state of Arbitrum for at least 24 hours, and then your node needs to sync. So we think 30 hours is a safe time period for a claim delay. So 30 hours later, someone makes a claim and they leave a deposit, and a challenge period begins. So in the happy case, after a challenge period, the claim is accepted, the deposit is returned to the claimer, and we accept the state of the Merkle root, and anyone whose messages are included in that tree can relay their messages. So in the unhappy case, if someone challenges the claim, they also leave a deposit, and then someone can call the native bridges to resolve this dispute between the claimer and challenger. Half of the deposit will be burned because the claimer and the challenger could be the same person. And the other half is rewarded to whichever party was honest. So the system is griefable. The system is permissionless and therefore griefable. So someone could make false claims and also challenge themselves, in which case they incur a cost because half of their deposit will be burned, and they slow down the bridge for a single epoch. But the thing is, the Merkle tree is growing in size, and it's storing all messages that have ever been requested to be sent from Arbitrum to mainnet. So this means in order to delay the bridge, you need to spend a deposit, or half of a deposit, every epoch. So you have this linear griefing factor. So one interesting parameter of the bridge is that honest parties need enough liquidity to challenge potentially malicious claims. So is this safe? Some of the implementation for Vea is related to a Ethereum research post that Ed Felten, the chief scientist at Arbitrum, posted about. And this is how to speed up or shorten challenge periods in rollups. So the idea is that since the merge, since proof of stake, since the merge, like consensus is sort of working like clockwork. So every slot time, there's an opportunity for a block. So the way it's working is that so Ethereum consensus has its own notion of epochs, and in an epoch, you have some randomly selected block proposers, and those block proposers, they could build a block, or if they, if their hardware is malfunctioning, or if they have some network issues, they might miss their opportunity to propose a block, in which case you might have a missing block. So the idea is that on-chain, you can look at the difference between the block number and the timestamp to check how many blocks should there be and how many blocks are missing. So why is this relevant for challenge periods for optimistic systems? Well, so there are some concerns about censorship. So if someone makes a malicious claim and an honest party actor wants to challenge that claim, that challenge could be censored. So this could be censored by block producers. So this is a type of censorship that Tornado Cash was experiencing, where about, like, at some point 50% or 80% of block producers refused to include any transactions to Tornado Cash. But, like, let's say 50% of block producers refuse to include transactions to Tornado Cash. That just means your transaction will take twice as long to be accepted. So that's one type of censorship that people sort of call, like, weak censorship. But another type of censorship that the roll-ups are worried about, and optimistic mechanism designers are worried about, is strong censorship. And strong censorship is censorship of block producers, not by block producers. So what this means is that a block producer might choose to include a transaction which will challenge an honest claim, but there could be some network-level denial of service sort of attacks, maybe Eclipse attacks, or other more sophisticated attacks at the network level, which will fork out a block that's been proposed. So this is very difficult to accomplish. There have been some sort of, like, academic papers or theoretical attacks on slightly modified versions of Ethereum consensus. But nonetheless, if you have an optimistic rollup where you have an escrow contract on mainnet that has, hundreds of millions of dollars of value locked, then you have an attack vector. So this sort of attack is not insignificant. So anyways, point is, if you have censorship of block producers, if you have blocks that are forked out, you can tell on mainnet if blocks are missing. And you can build a statistical test of whether or not you think forking censorship is going on based on a risk tolerance. So what's an example? Okay, here's some complicated equation. It's a statistical equation. But the point is, we can calculate for, let's say, you assume that 10% of block producers will not censor your transaction. Then you can build a test which says something like, in a 2-hour time period, if there's more than 34 blocks missing, then there's a 1 in a million chance that forking censorship could be going on. So this sort of statistical analysis can give us a test customized for our risk tolerance of whether or not censorship is going on. So here's like some statistics about Ethereum and Gnosis. They share a similar consensus system. They differ that Gnosis chain has a slightly different slot time. So what you see here is that the first week after the merge, about 1% of blocks were missing on Ethereum. So this could be, validators being offline or network issues. And 2 months later, 4 months later, you have better performance. Fewer blocks are missing. And then recently, after the Shapella hard fork, you had about 5% of blocks were missing. Actually, the first day, in the first 24 hours after the Shapella hard fork, there was like 10% of blocks missing, so block producers missing their slot to propose blocks. So what's the point here? With a censorship test, we can develop a criteria that says something like, in a given time period, if more than 2% of blocks are missing, then we should slow our system down. Then we should call the native bridge and we should wait for 7 days. Otherwise, we can go ahead with our 2-day bridging time. What this means in practice is that probably after hard forks, the system will slow down. And once block producers have a better network performance, the system will speed up again. And we can do the same thing for Gnosis, develop a test that, in Gnosis' case, the sensitivity of our test is dependent on already the network performance of block producers. So for Gnosis, we can say if more than 5% of blocks are missing in a given time period, then we slow the system down. So we slightly modify the happy path, which is just that after a challenge period, we accept a claim only if the censorship test passes. So just to summarize some features. So features of Vea. I try to like put things in a positive light because oftentimes people use like a negative language to say what a system is not. So, but I'll provide a translation, you know, so it's more common for crypto natives. But yeah, so anyone can force the correct execution. So, in other words, translation, it's a one of n security or trust assumption that you yourself can be the honest participant in the system to force the bridge to execute properly. The system is inclusive. So, translation, it's permissionless. Anyone can participate. It's not closed off to a small set of validators or operators. The system is permanent, or in other words, immutable and ungoverned. No governance parameters, no governance token, immutable contracts based on these safe parameters that are set when you deploy the contract. So, you know, and in line with that, it's a public good. So there's no token, no rent seeking, no fees. But because it's an inclusive system, delays are possible. So the system is griefable. Attackers can spend deposits to slow down the process. But the cost of that delay grief will increase linearly, and they can only delay the process a maximum of the time it takes to call the native bridge, which takes about 7 days, 8 days for optimistic systems. So this sort of system can be used to send messages between rollups and different chains. So in particular, what I'm showing here is that the $sign shows you that using Vea rather than the native bridges is cheaper, much cheaper than going through mainnet, because you don't pay mainnet gas in the happy path. Or if there's a challenge, it's very clear who's paying gas fees, because the challenger will reward whichever side is dishonest, either the claimer or challenger, they're compensating the other honest party to pay for the gas fees to call the native bridges. But in any case, in the happy path, you don't go through mainnet, so it's cheaper. So for example, between Arbitrum and Optimism, it's both cheaper than going through mainnet, and it's faster. So in the happy path, 2 days. And in the case where you're bridging from an optimistic rollup to Ethereum, for example, the settlement layer, it's fast. Not necessarily so much cheaper than going through mainnet. It's about the same cost. Going from optimistic rollups to Gnosis chain, well, it's both cheaper and faster because, well, block space on, yeah, there's more block space on Gnosis, less demand. It's probably going to stay that way unless there's some crazy NFT airdrop on Gnosis, in which case demand for block space is really high. Could be more expensive on Gnosis than Ethereum, but yeah, basically should be much cheaper when the destination chain is Gnosis. The idea is in the happy path, you only pay gas on the destination chain. You never pay gas on intermediary chains or Ethereum L1. If you're bridging from Ethereum, you don't really have a benefit. Just use the native bridges. You don't really have a big cost or speed benefit. If you're bridging from Gnosis to some of these optimistic rollups, well, you can save some transaction fees, but the system isn't necessarily faster. So basically, this system is like Vea is a good design for an optimistic bridge between optimistic rollups or sending messages from and to optimistic rollups. Right. Yeah, we're working on the testnet deployment, and we want to prioritize maybe bridging to Gnosis first, and then we'll see about other chains that there's sufficient demand to operate. And we're working on Vea Scan, a way to view your messages and see claims that are being made. So that's pretty much it. What I want to invite, like, anyone listening to the talk is that, like, if you are working on a protocol that needs some cross-chain solution, then consider, yeah, if you're interested in this sort of bridging approach where you concentrate your economic security on a single chain and just do message passing, there's no tokens being sent around, we're just sending messages about outputs of the oracle that, you know, if your protocol is interested, then you can participate as a watcher or validator of the bridge. You can be your own security for the bridge. And if you're building some applications, cross-chain applications, you could build liquidity networks on top or cross-chain governance. Nonetheless, the system works with one of n trust assumptions. So, you know, even if Kleros is the first user of Vea, and Kleros will operate, be one of the bridge operators, running a watcher that's checking for fraud and making claims about the state of the Merkle root. Basically, if other developers want to use this system and the protocol, you get your messages relayed basically, well, in a sense for free. But if you want to participate in the bridging process, then you need to run your own watcher. If you want to be the one of n honest parties in this optimistic system, you have to run your own watcher. But otherwise, you know, we will be running this bridge. And if you are developing a cross-chain application, you can write your own gateways to bridge through Vea and get your messages passed basically with no extra cost. Yeah, that's pretty much it. Thanks.
Hello. Okay. Let's thank Shataro's talk. And does anyone has questions here?
Thank you for the very insightful talk. Would be curious to learn a bit more about, so the dynamic challenge period would be like reactively adjusted according to on-chain like status or on-chain, the state of the chain. Are there any risks to it being a reactive approach versus being a preemptive adjustment before like all the missing blocks, before all the potential censorship? What are the risks involved, and are there any good ways to like counter them?
Sure. So, right. So the question is, what are the risks involved in using a dynamic challenge period? Specifically, like in this case, dynamic means you either have this fixed challenge period, which right now we're using 6 hours, versus using, so the challenge period is 6 hours, or you have to call the native bridges if the censorship test doesn't pass. So actually, the challenge period isn't really dynamic. The challenge period is fixed. The challenge period is 6 hours, but if someone doesn't make a challenge, you can't optimistically verify the claim. So you have to use the native bridge in order to figure out the results of whether or not we should accept the claim. So like, yeah, at a high level, you could think that the challenge period is sort of dynamic, but in reality, the challenge period is fixed at 6 hours. It's just, if there's no challenge after 6 hours, we don't accept the optimistic claim as true and verified. We also check if there are missing blocks. So it's not exactly a dynamic challenge period. Yeah.
Any questions? No? Okay, let's thanks to Shataro again. And before you leave, two things I would like to share. One is our afternoon section start at 1 p.m. here. And the second thing is we have a beer party at 12:30 in the second floor of Building M. Just right, just next by our check-in counter, 12:30. And